Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss about the shear stress in turbulent flow. So in our previous lectures, already we have discussed about the laminar flow, transition flow and turbulent flow, which is based on the Reynolds number actually. And the Reynolds number is defined by the inertia force by viscous force, and how to calculate the Reynolds number by this formula we can calculate rho Vd by mu, or we can say Vd by nu. This is the equation for the Reynolds number. So when the Reynolds number is within 2000, then it is called laminar flow. When the Reynolds number is 2000 to 4000, it is called transition flow. And when the Reynolds number value is greater than or equal to 4000, then it is called turbulent flow. Okay. Now, in previous already videos we have seen, okay, the shear stress equation for the fluid flow. Okay, so that one we have seen. This is tau equal to mu into du by dy. We have seen this equation during the Newton's law of viscosity. So this equation was derived by the Newton's law of viscosity. So this tau v I have given here, this term v, okay, the shear stress due to the viscosity. That's why I have given here tau v equal to mu into du by dy. Mu is the viscosity, this du by dy is the velocity gradient. Okay. Now this equation was given for viscous flow. Correct. So viscous flow is nothing but is known as the laminar flow also, because when the viscosity of fluid is more impact, then in that condition your velocity, your flow of velocity will be very less, and that in that condition we can consider this is a laminar flow, because in this equation if you see rho Vd by mu, the velocity is the key factor here. Remaining things are constant. Rho is density constant, diameter is constant, mu viscosity is constant. Velocity varies means your Reynolds number will be varied. So this is the key factor of velocity. So in the viscous flow, okay, your velocity will be very less. That's why it is called as for the laminar flow. Okay, but when the topic is coming for the turbulent, in that condition this will be not suitable for this application. That's why similar to this equation, another one scientist, his name is J. Boussinesq, B-O-U-S-S-I-S-Q, Boussinesq. Okay, J. Boussinesq gave one expression for the shear stress for the turbulent flow. Okay, and that equation was written in this form tau T, because shear stress for the turbulent flow, and here it is given this is eta, and similar to this del u by del y or du by dy. Okay, and this is u bar. Okay, this is u bar. This one you can give for this equation 1, Newton's law of viscosity, and this is the equation for Boussinesq equation. This is Boussinesq equation, this one. Now at this condition, if you see the terms, what is there? The eta term is there. This is tau t. This is very simple shear stress for the shear stress due to that you can write turbulence. This is shear stress due to the viscosity, viscous flow or viscosity you can say. Similarly, this is the shear stress due to the turbulence you can say, and this is eta. Eta is the new term here, so you can write eta equal to, this is AD viscosity. This is AD viscosity. Now similarly here viscosity of the liquid was there. Now here it is AD viscosity, because ADs are formed during the turbulent flow. That's why this AD's viscosity is considered here, or it was mentioned here. Anyway, next is U bar. If you see the U bar term is there, this is bar means it is nothing but the average. So this is nothing but the average velocity, okay, from a distance of some distance from the boundary, that need to be considered actually, because we have seen when the liquid will be flows over the surface. Okay, suppose liquid is flowing, if it is a open one, then we can see like from this zone, at this zone, as we know that near to the boundary the velocity value will be 0, and slowly it will be increased. Okay, and this average velocity is talking about at this zone. Okay, apart from this boundary layer. So this is the average velocity with some distance that we need to consider, which it can consider in the y distance, suppose, because in the y direction we need to consider, not in the x direction. Okay, so the average velocity at a distance of y from the boundary, you can say. Okay, average velocity at a distance of y. Anyway, so this is the expression given by the J. Boussinesq, okay, to derive the shear stress for the turbulent flow. Okay, as I told, this is AD viscosity eta. Okay, so the ratio, okay, we already know that previously viscosity equal to, one is viscosity mu, this is dynamic viscosity or viscosity, another one is nu. Okay, so nu is the kinematic viscosity. So here also the kinematic eddy viscosity is denoted by the ratio of eta by rho. Eta by rho. Here also we know that kinematic viscosity, if you remember, this is mu by rho, viscosity by density. Similarly, the kinematic eddy viscosity is nothing but the eddy viscosity divided by the density of the mass density of the fluid. So this is known as the kinematic eddy viscosity. Okay, and here it is not denoted by this nu term. This is denoted by epsilon. This is denoted by epsilon, not eta. Eta is actually for this kinematic viscosity, and here epsilon equal to this term. Okay, epsilon equal to eta by rho. This is another one term, you can just highlight it. Okay, why I told these things? Because sometimes it is also required when we are talking about the viscosity, then again sometimes kinematic viscosity is also required there. So here also when you are talking about the eddy viscosity eta, and simultaneously we need to consider the kinematic eddy viscosity, which is epsilon. Okay, now if the shear stress due to the viscous flow is considered here, this one, okay, and the shear stress for the turbulent flow is considered, then what about the total shear stress? What about the total shear stress can or became, we can write, this is, we can write tau equal to, we just need to add these two things what we got, equation 1 and equation 2. This is tau v and tau t. Shear stress due to the viscosity and shear stress due to the turbulence. So this one is just write this equation, nothing but mu, you can write du by dy plus eta du bar by dy. This one we can give equation 3. Now if you see this equation, the values of eta, equal to 0 for what? Now for laminar flow. The values of eta is 0 for the laminar flow, as I told, because this eta term is going to be used for the turbulence condition. For laminar condition it is not going to use. Okay, but this eta can be varied. This eta value can be varied 1000 times. Okay, 1000 times of viscosity. This eta time is varying 1000 times of viscosity. So to find out this shear stress, if you see the shear stress, to find out shear stress for the, especially for the turbulent flow. Okay, especially for the turbulent flow, to find out this shear stress for the turbulent flow, this equation, if you see, what equation is given? This equation. In this equation, if you see, tau t equal to eta du bar by dy. So this eta value, this eddy viscosity, if you see, it cannot be predicted. Okay, this value cannot be predicted because it is 1000 times of viscosity. Okay, there is no certainty, there is no certain value for this eta is there, as it is 0 for the laminar. At least some fixed value should be there for the eta, so that you can identify this shear stress for the turbulence flow. So due to this condition, there is no certainty of this eta value. So this shear stress, how to calculate this one? Shear stress for the turbulent. So due to that, it is having a limited use. Very few use are there for this. Okay, very a small restrictions is there in this uses, we can say that one. Okay, so this shear stress for the turbulent flow as per the Boussinesq equation, it is having a limited use. Okay, so to overcome this problem, actually another one expression was given by the Reynolds. So Reynolds again given one expression for the turbulent for the shear stress. So that is actually at in the year of near about 1886, I hope. At that time, this Reynolds developed an experiment or expression for the turbulent flow, and that is actually how it is, like previously how it was given, like by taking two different layers. Suppose this is at the you can say not y direction, this we can consider the v velocity, and this one we can consider with respect to some time, you can consider here. Okay, and this is some space is there, suppose. Okay, this is velocity, yeah, and this is time, suppose. Now between these two layers, actually this Reynolds when it is given this turbulent expression, now based on by taking two different layers, suppose different layers of fluids are there. Now see, when the liquid is flowing or the fluid is flowing, we have several layers of liquids are there. Okay, so by considering two layers of a fluid, suppose this is the two layer, this is one layer and this is another one layer. By considering this two layer, so this is what will be the height of this. Now obviously there will be height of dy from this liquid layer to and from to this liquid layer. By taking this small distance, okay, so Reynolds given one expression, this is tau equal to rho into u dash v dash, rho into u dash v dash. See, what is the u and v? Now u and v is nothing but the velocity in the x direction and the velocity in the y direction. This is suppose x direction and the y direction. So what about the velocity at this x direction? Now let's consider this is u dash. And what about the velocity in the y direction? Let's consider this is v dash. So by considering this term and conditions, he gave this equation, this one. Okay, now so this u dash and, as I told, u dash and v dash are the these are the fluctuating component of velocity, you can say. So this is nothing but u dash and v dash are the fluctuating, these are the fluctuating component of velocity. Why it is fluctuating, I'll tell you. Fluctuating component of velocity, actually, because it is, see, when it is turbulent flow, when you're talking about the turbulent flow, the fluid will be very fast, the velocity of the fluid will be very fast. So the fluctuation, actually, it is, so this one also we can give. Okay, so here actually this one we need to consider in the x direction and this is y direction we can consider. So the same velocity time, I will draw it again, another one equation for this fluctuating components, actually. So this is we need to consider with respect to time. So here we can, as I told you, x direction and y direction we can show, and this direction of this fluid we can show here. So here you just can we can consider x and y direction on behalf of this time and velocity. Okay, so here we can give the velocity and time, and this what is this fluctuating component? Just I'm explaining. This fluctuating actually refers to the variation of fluid over a time and space, velocity of fluid means what is the, suppose this is the velocity of the fluid, this is given, and let another one draw another one line. So this line, this velocity of line, okay, this indicates for the laminar flow. That means the velocity of the liquid is constant over the time period and space also you can consider. But here if you consider for the turbulent flow, in the turbulent flow, it will be not in the similar case. The fluctuation or the fluid movement will be in this way, like this. So there is you can see a wave structure is there in the fluid flow. So this wave structure is nothing but, you can say, so this is the line what I have drawn here. This is actually average velocity. This is actually average velocity u bar, I can say. Okay, this is u bar. And another one thing is there, that is u. See, already u dash is there. U dash is nothing but, as I told you, fluctuation component of velocity. Here it is u bar. U bar is nothing but the average velocity of this component. Here if you see, okay, and instantaneous velocity, this is ui. This is ui. So this u instantaneous velocity is nothing but, okay, let the value in this conditions, the value of this velocity of this liquid at these conditions is instantaneous velocity, and the average of this velocity we need to consider u bar. So this we can consider, see, u or v, anything will need to be considered here. So here we can write, this is the fluctuation velocity u dash equal to, we can write instantaneous velocity, how much? Now what is the highest velocity will be there, suppose that is uy minus u average, so that we can find out the fluctuating velocity. Okay, now though you can see here there is a disturbance is there in the velocity, so here also, you know, we need to consider as a x direction and y direction both. Okay, so the tau equation, if you see the tau equation, we can give a equation number 4. This equation of shear stress or tau is dependent on the u dash and v dash, because rho is there, rho is density of the fluid, so that is fixed. So it is purely based on the u dash and v dash. Now again that was realized that, okay, so if this fluctuating velocity u dash and v dash will vary, then obviously the tau is going to be vary. Okay, the tau is going to vary, because this is the velocity in the x direction, this is the velocity in the y direction. If this is going to vary, then the tau also going to be vary. The time average, because the time what we are considering at the time, because as I told you, with respect to time and space, the time average, the both side, if you see at this both side of the equation, if you take this time and this for this time also, okay, then because this is also not going to satisfy. Why? Because there is a changes of velocities, changes of, you know, x direction velocity and y direction velocities. So again what it was done with respect to considering the time, okay, the time taken, this was again written u dash v dash bar. Okay, so this is the tau bar equal to rho u dash v dash bar. So this is nothing but the average what we have taken. So this is also called as Reynolds stress. This is also called Reynolds stress. So here also, if you see, we are not able to going to identify the exact value of that shear stress. So here also we are going to consider some average velocity of that, you know, that fluctuating velocity, what is the average value is there. Previously what we have taken, only fluctuating components velocity we have taken. Now what we have taken here, what Reynolds was given this experiment expression on behalf of u dash and v dash is just given a average of that, bar of that. So that's why the u bar equal or tau bar equal to rho u dash v dash bar. So this is also known as Reynolds stress. Okay, so I hope you understand this concept. Okay, what is the, you know, expression for the shear stress in the turbulent flow, because based on this the Reynolds experiment also was derived, because it was, this expression was given by the Boussinesq equation, and while this is given by the Reynolds expression. So I hope you understand this concept. If you are having doubt regarding this, you can give a comment on the comment box. Thank you all.